Once again, not once again, good afternoon, everyone. Okay, so we are meeting first time in the afternoon. So now we will go ahead with our next session. This is based on tutorial. So in this tutorial, we are going to discuss about this thin film deposition, how you can make a thin film. First of all, what are the equipment currently which we have here. So on that you can see that facility and how we can make the thin film based on this chalcogenide based devices. And if we want to take their resistivity measurement, so how we can perform that thing. So on the basis of these things, just I will cover few aspects. So first part that will be the resistivity measurement of thin films, and then thin film deposition in. So this will I will discuss here first part, and the next second portion will be demonstrated in the laboratory. So we can identify in which way we can cover these aspects. So if we talk about this phase change memory, so again just have a quick recap. The thing probably we have witnessed so many times these things. What are the phase change material and the style line, and what are the principle of these phase change materials, set, reset, and all those things. So based on that, we need to understand how you can deposit this film. So there are multiple techniques are available. PVDs based techniques, it is already there. Some thermal evaporator based techniques, sputtering units, and if you go some higher sides, so ALD deposition is also there, molecular beam epitaxy. So based on that, you can coat these chalcogenides. Based on the appropriate composition, you can deposit these thin films, and then accordingly you can characterize. So for deposition of these films, based on the elements, you can identify the suitable composition, and then you can deposit. So I would say this is one of the important thing, because if we are not able to calibrate material properly, then how we can go further for device level characterization. Okay, so this is the very important aspect: material fabrication, material deposition. So in that level, you need to first identify the suitable technique, suitable deposition method. On the basis of that, we can see these things. Okay, so for this characteristic, for amorphous crystalline, all those this functionality, if you want to see these things, this performance, so you should have a samples, you should have a material, then only you can identify this. And these are the elements. So these elements we need to prepare. Okay, so for that we have a suitable appropriate technique. So as I talked about this multi-bit PCM technology, so you are knowing this two phases are there. Based on that, you can identify these. If you easily tune, then you can see this multi-bit state, all those things. So this is the material property actually, where you can tune this, where you can identify, and based on the number of levels, you can say that yes, this is the number of bits are available. Okay, so the overall thing is that this resistance, to identify the resistance of material is also very important. Although this is the programming curve, but initially how the material is performing, what is the resistance, contrast, so that is very, very important. So for that, you need a resistivity measure, identify the thin film. This is the prior and most important thing, is that to understand how the material contrasts. So after identifying the material, you know, first you have to identify their resistance, contrast, and with the help of that measurement, you can also identify the crystallization temperature also. So as we know, this large resistance contrast allow multi-bit programming. So we need to identify large resistance contrast. So that we need to figure out with some kind of instrument. So this is one of my work actually, which is earlier reported for this resistance measurement setup where we can identify these uh, setup where we could calibrate or we can measurement the resistance of thin film to identify their resistivity. So as you can see here, it is kind of a tubular furnace, and where in between it's a kind of a tube where at the center of this setup, this your sample is placed. You can place your sample, and then it could the value of resistance can be directly measured into this computer. So what are the instrument it is uses here? So this overall setup, it is connected with SMU, source measure unit. So this source measure unit, it is going to provide you the resistance value, okay, resistance value of your thin film. So how it will do, we will see this thing. So this is the electrical setup basically. And then along with that, you have a switching network. So switching network is that it is having a special purpose for measurement of this thin film. So this is, it's a kind of a switching. It is switching the terminals. And then to automate this setup, you have here you can see this data acquisition system is also connected, and it is interfaced through computer. So the thing is that this computer is going to operate or going to automate by the help of this this DAC to make automate this switching network, and then appropriately this terminal you can change from here. Okay, so how this thing we will see in the subsequent slide, but just try to have a overview of how this thing is developed here. And then this whole thing is fully automated by computer, because you need to identify in situ measurement. You are heating the sample, and then simultaneously you are identifying the resistivity also. So this is the overall way by which we can see this. So what method actually it is identified here? So if you see the whole setup, the thin film of this material, it is identified using this Van der Pau method. So Van der Pau method is are reported long back in 1958, as you can see by this Phillips research report in 1958. So they have proposed one method to identify a resistance of any non-uniform sample or any sheet, I would say. It is not a kind of a linear resistance where you simply apply voltage and simply get a current or resistance. It is not like that. It's a kind of a sheet. It may be uniform also, it may be non-uniform also. So that based on that, you need to identify these things. So to get more idea about this method, you can refer this work. So it's a kind of they have proposed this mathematical relationship, where we can see this resistance of Ra and Rb. So this is kind of a different configuration in Ra and Rb. So Ra is what? First you are sourcing this side and measuring this side, so you are getting one resistance, okay. And on another side, if you see, you are just changing the terminal of source and measurement, and then you are getting Rb. So this Ra and Rb, yeah, that we can identify. And when you solve this equation, you can solve this equation using some mathematical tool and all. You can simply, if you are able to identify Ra and Rb, you can directly solve this equation for RS using MATLAB, and even you can solve mathematically also. And if you have the thickness of this material, so in that case you can see and you can identify the resistivity of this material. So it's a kind of a method by which we can see the resistance. But how they have proposed this? So to get more idea about this, you can refer this paper, and I can also give you brief idea about this, what is this method and how it works. So you can see here. So if we talk about this method, so this method, so based on this method, this mainly developed this method in this by this report. to measure the resistivity of thin and flat sample of semiconductors. So if we have a thin film of any sample, so to identify their resistivity, as you can see, and the van der Waals technique for resistivity measurement allow avoiding problem due to incorrect knowledge of sample geometry. So if you don't have any knowledge of any geometry, whether it is linear or what kind of sample is there, so you can simply place this contact at the edge, and you can do multiple measurement, and they have appropriate mathematical equation, and you can do this. So, but there are certain assumptions. So the assumption is that the contacts are on the edge of the sample. Okay, they have done some kind of assumption, and then the contacts are sufficiently small, and the surface of the sample is simply connected. It's a kind of some metallic content, and it should be connected. So by which you can see. And based on that, this method, you can get this resistance value. Say suppose I am telling you are sourcing is this particular terminal. If this is your sample, and you have identified 4 contacts at the corner. Say suppose this is your sample, I would say, okay, and you have identified these 4 terminal. Say this is your thin film or deposited coated any film, whether it is through spin coater or thermal evaporator, or even for the sputtering unit. So you got any film or any size, and you can place such kind of contact. So if you are sourcing these 2 terminal, and you are getting bias on another side, so you can get this resistance kind of a V by I, this relationship VPO by I. Okay, so it's a kind of, so what is the thing basically here? So the thing is, first you need to identify the current density, and based on this mathematical equation, you can get the current density and then radial electrical effect. Okay, so after solving this equation, you can get proper understanding about the resistivity of, because ultimately it is the relation between current density and radial electric field, which is very, very important. Then if we know the potential drop due to this electric field, okay, and this is kind of a potential drop due to this electric field, if you are able to identify, and then if you are able to properly, you can solve this mathematical equation to identify this relation with respect to this radial bias, I would say, because it is not simply voltage, it's a kind of a, you are calculating with respect to field and that radial change. And then after solving these equation, you can directly identify these resistance value with respect to this identified contacts at the edge of your thin film. So this is mathematical equation. I am not going much inside into that, but you can refer this work where you will get more. They have solved everything with respect to their assumption. Our main focus is that how we can get the sheet resistance of any sample, which is very, very important, because our ultimate goal is that we are identifying any method and we are getting those. So it's a kind of some mathematical relation where you can get a potential drop due to current leaving at point, and then we can get the desired value of resistance with this mathematical expression. They have some logarithmic values here with respect to this bias and current. And then finally, if we will able to identify, so after solving equation 7 and 8, 7 and 8 means what? 7, if you see, this is RMNOP, and this is another is RNNOPM. So what is this? It's a kind of they are changing the terminal of source and current, and then they are identifying this relation. So if you are able to solve this equation, so you will be able to identify this rho s value. This is kind of resistivity, and this will be helpful to identify the resistivity value. So this is a kind of a configuration which I was discussing about that. So where this van der Waals resistivity method, so this is the 4 configuration, different configuration. So these two, where here you are sourcing, here you are measuring, here you are sourcing, here you are measuring. So these two more or less same. Why? Because it is identifying the reciprocity theorem. Okay, so this is after averaging out this value, you will get 1 RA, and if you average out these two value, you will get RB, and you put simply in this equation, and you can directly get the seat resistance value. Okay, so this is the way by which we can calculate the resistivity, and we can identify the method actually to get this value. So we were here. So this is the mathematical equation. So our main focus is that we are not going to do the research on that what they have. We have simply taken this value and we can further identify that. So now here important thing is that how you can get these two value. How you can do this value. So have you earlier done any this measurement? People who are working in this direction. Anybody? Have you earlier measured thin film resistance? Huh. So how you are?
We took the 4 points on the thing, and then we source the current in different direction from A to B. Then measure it from C to D. The voltage we measure from C to D. In the other case, we do the reverse part of that. So then we get two values of the resistance, RA and RP. Then we average that.
Average value. Okay, okay. So how you are changing the terminal? How you are changing the terminal? You are getting making two value, and then you are averaging.
Yeah.
So how you are getting that value?
We were getting 8 values of resistance.
Yes, yes.
So they were 1, 2, 3, 4, 2, 1, 3, 4 kind of combination. Then we average that value.
Okay, okay, okay. So I'm curious to know, I would say, how you are changing the source and sense terminal.
So it is like that we keep the source at same location. Only what we do, we change the directions.
Okay, okay.
We have 4 manipulators.
Yeah.
We only change the direction of the current in the source we supply. We only change the direction.
Only changing the direction. Yeah. Okay, okay.
We have 4 SMU.
4. Okay, 4 SMU. Okay, understood. Now understood. So here, what we are doing here in this case, just we can use it. It's a kind of a switching matrix, low cost switching matrix. It is just provide us, simply you can use the relay, and you can control this with data equation, and this is the setup with, you can connect your one SMU, and it is provide us the beauty so that you can change the terminal. So this is the thing. So here this connections are coming for your source and sense, and here for your sample it is going, and through this data equation, NI based data equation, you can control and you can get that. So this is it's a kind of a custom built switching network, and the data equation setup which is reported in this work, where you can see with respect to that SMU, just to change the terminal and to identify the resistance value. So this is the pictorial view graph of this switching board, where this kind of a relay is there, and it is connected with transistor. So it is going to operate through this control signal, and based on the appropriate circuitry, you can easily provide your control here, and then you can see. You can source, I would say, the current here, and you can get desired voltage value after changing the different directions. So this is the circuit diagram of this switching network board. And then if we try to figure out the connection configuration, so it's a kind of a 4 configuration. You can enhance this 4 into 8 also, the way we can get. So 4 values you can average out, and then remaining 4 you can average out, and then you can directly get this value. So here this method which we can use, that where 4 configurations are identified, where you can see how it is programmed. So for connection configuration 1, what are the relays are operated, as you can identify that, and what are the desired output you are getting. So based on that, you can operate these value, and you can see the resistance value, and then further you can average out the corresponding values, and then you can get value. So the thing is that here the status of your relay, basically, to get a particular connection. So this is the thing, and this is the program algorithm which is programmed through LabVIEW programming, where the whole thing is controlled to identify these values, where we can just apply a source current value and it is calculating the voltage, and then after it is providing the appropriate connection, then a further measure, and then again activating switching network. So four, as we are getting four configuration, so four type of measurements are there, and then finally we can get average resistance value of this. And after identifying this appropriate mathematical formula where you can directly get this value, seat resistance or value, after providing the value of Ra and Rb, as you can see here. So this is four values you are getting. So similar value you can average out, and then you can get a particular resistance value, and you can use this value to get the seat resistance of your thin film. And if you have the thickness of your film, you can directly get the resistivity. So this is the way by which this instrument is working, and this is the overall setup, this front panel of that program, where we can see. So this is kind of a material, phase change material, which is showing the the resistivity change, resistance change, I would say, with respect to temperature. Okay, so the thing is that we can identify this resistance contrast first with this. Okay, and another thing is that the crystallization temperature we can see with this. So using this measurement, you can directly calibrate your material first of all, because crystallization temperatures is very important. So we can get the crystallization temperature with this, and you can also get the resistivity contrast for your chalcogenide based material. So this is the overall setup by which we can see the change in resistance value and the crystallization temperature. So this is the overall thing related to your temperature dependent resistivity measurement setup. And another topic just I will move. So this is the thin film deposition setup, so which we have in our lab. So this is the multi-target magnetron sputtering unit which we have in our lab. So just I will brief you here little bit about this setup, and then you can have a quick round on that. So the thin film which we can fabricate with this. So this setup is having basically RF source, and along with DC source also have, and the source number which is having, we have two sources. So on that you can provide, you can do a single element deposition also, and if you want to do a co-sputter deposition for phase change material, and after optimizing the power and the chamber inside the environment, I would say, and so that you can properly calibrate this system. So what are the important parameter here? First, the power, how much power you are providing. Based on that, everything is dependent. Okay, if you want to get a more thickness, or if you want reduce the thickness, or if you want uniform, everything you need to calibrate first of all. Same material can deposit at 20 watt also, 40 watt also, but there is a difference. Okay, that we need to identify using structural characterization, material characterization of the thin film, and then based on that we can do. Another thing is that deposition rate. So this deposition rate, if we see, so how you can identify the deposition rate. So for deposition rate, what we can do, you can deposit this phase change material, and some advanced setup they have directly some kind of instrument inside, and they can directly calibrate you. But further also you can have some understanding about the thickness, or you can do reflectivity measurement, you can do some AFM, cross section FECM, and then you can see how much the thickness you are getting with respect to your sample, and then you can calibrate. Then you can get the deposition rate. That same condition you need to fix multiple time, you need to do this. Okay, once you calibrated one material, this is the deposition rate, and then you do multiple time measurement with same condition. Same condition means what? The here it is not mentioned. You can see there the value of how much you are providing the argon, first of all, inside. What is the pressure? Chamber pressure is there. The chamber pressure also you need to calibrate. Everything is dependent on that, and if all parameter is constant, then only you will get a uniform deposition. Okay. Next is that rotation of substrate. So rotation of substrate is also very important. If you make the rotation very fast of your substrate, so you may get change in the film quality and uniformity. You will get. So you need to optimize in appropriate substrate rotation, so that it can be helpful to get the uniform thickness. Because when you have the confocal arrangement in your sputtering unit, where it is kind of tilted with some angle and then rotation it is providing, I will show you. So in that case, this substrate rotation is very important to get a uniform film and uniform thickness. So this is the I'm briefing you. So we can you can check the deposition also and some kind of a plasma as well. So this is it's a kind of just view graph. Just will discuss about the principle, how the sputter deposition works actually. So if we see, this is the chamber. This is the chamber, and it's a kind of you can see your target is here, and from here you are providing the RF power. Okay, this is the RF power you are providing, and this is the chamber. So chamber, this is for vacuum. So you are continuously connected with some kind of a turbo pump or some vacuum pump, so that the whole particle can go out. You need to make chamber very clean, then only you will make the deposition. Okay. And then one side you are making the incident ions. So incident ions means argon we are purging from here. So what happens, the moment you are making, first you are creating a vacuum, then you are closing this, and then you are providing the RF power and you are purging ion. Sometime you need to release this also if it is very dense inside argon is there. So what will happen, this argon atoms are getting hit, okay, on this target. When is hit into this target, so the atom, this particular atom, this green one, it is getting out, okay, and it is going to stuck in the your substrate. Okay, so this process, this is the inside, it is happening, and when this process is happening, here you can see some kind of a color. Okay, so that color called as a plasma. Okay, so that plasma, you can easily see this plasma, and that plasma is nothing but it's a kind of the particular your atoms it is showing that, and or another word you can say it's a sputtered atoms which is going towards the anode, and it is providing us the thickness, or it provide us the thin film. Okay, so this is the way by which this sputter unit works. But after looking into this, it is not, you need to calibrate. First, lots of conditions are there. This argon pressure, RF power. Sometime if you want reactive sputtering, so you have some another this inlet kind of thing where you can provide some nitrogen also. You can put nitrogen doped. You can, if you want some kind of oxygen, you can provide oxygen also inside the chamber, and then you can do some kind of a deposition based on these things. Okay, so this is the overall idea. So advantage of sputtering deposition is that it is a widely used PVD technique. So PVD technique is a wide term, physical vapor deposition. So there are techniques on that available on that. So it's a classification. So on that, this sputtering is coming into that. So it's favorite industries like microelectronics, optics, material science for precision and versatility. So from sputtering onwards, industry are accepting yes, these films are uniform and some kind of and some more advanced research for ALD and some kind of there. So where industries are more having confidence on the thin film deposition. So this is some key benefits of that. So some kind of a high purity films, precise thickness, and uniform coating, and this wide material compatibility, strong adhesion. So you can go through with that. this is it's a kind of a metallic property why we are using this. So possibly I will provide some notes on that, so you can go through with that what is the main important point behind this sputter deposition and all. Okay, so my this discussion part of here, just I'll stop here, then I can take few questions. If you have some questions, then we'll move towards our laboratory, where we will see the real experimental setup, so that you can have more feeling, more understanding about that. So I can take one or two questions. We need to wind up then we need to go there also in laboratory. If you have any questions. Yeah. Target. So for target, we can do either, we can make a powder. Okay, just we can take a powder particular this material. Okay, and if sometime appropriate composition you can directly get. Okay, so this is bit difficult method, and you need to make kind of a inside furnace and everything. You need to heat up, and some pellet and all you can create bigger, but this won't work actually. So you can directly purchase from vendors. You can just provide your appropriate composition. If you have do on research on target thing, you can do that. It's not different composition you need to make, and there is process you need to make as per, say suppose in this sputtering you have 2-inch this cathode size, somebody is having 3-inch. So based on the size you need to prepare, so accordingly, because if you need a precise control on stoichiometry, so you need to there are vendors are there, so you can get that appropriate composition, and then you can do research on that. Yeah, backside. Anybody else? Any query? Any questions? Okay, so if not, then rather we should move towards laboratory. So you just go there and just see the instrument, and possibly we'll try to show you the deposition also, deposition of any material, where you can see the plasma and just see the sputtering setup, what are the components are available, and how we can prepare a chalcogenide based thin film. Okay, thank you. Okay, let's move towards the lab. Okay.